Hi students, in this lecture I am going to discuss LR circuits. Let us see. So we are focusing here, taking now combination of inductor and resistor. So connect now an inductor and a resistor connected to a battery. Initially switch was opened. So take battery's EMF as E, inductance L and resistance R. Okay. Now let us close the switch when time t equal to 0. That means initially there was no current in the circuit. Now we are closing the switch when time t equal to 0. So now we want to see how current is changing as a function of time. This is what we call growth of current. Let us see how to calculate. So once switch is closed, so what happens is current starts increasing. Okay, you just observe carefully. If we are not having inductor, current will increase from 0 to E by R immediately. I am repeating. If we are not having inductor, once we close the switch, current increases from 0 to E by R immediately. But because of inductor, what happens is it does not rise to E by R immediately. It takes some time because it is now opposing the change in current, but not current. Okay. So we have learned that inductor opposes change in current but not current. That's why current takes time to reach its peak value. So initially zero. Finally, what happens is after a long time, it becomes E by R after a long time. Okay. But to reach this value, it takes some time because of its property of inductance. Okay. That's why we want to see now current as a function of time. Now see what we can do. Current flows now like this. It is a clockwise. And the current is now increasing. So since the current is increasing, inductor tries to oppose the change. It is now increasing. Therefore, it tries to decrease it. Okay. Therefore, if you want to replace inductor with an equivalent battery, and that battery should be placed like this. It has to oppose. Since current increasing, it tries to decrease it. So this is now that battery. And for this battery, EMF will be L into di by dt. Okay. So now question is just like there are two batteries. This is battery one and this is a battery. And this is now resistor. Right. Let us see now how to take loop equation for this one. Kirchhoff's second law. Suppose I'm starting from here. Let us take it is a clockwise path. Then see what happens. We are moving from high potential to low potential. So I am writing here minus L di by dt because moving from high potential to low. That's why minus. Next, we are moving along the current flow, right? So here also what happens? Minus I into R along the current. Next, coming to here, we are moving from low potential to high potential. So it is now plus C, that is equal to 0, right? So simply replace the inductor with an equivalent battery. Once it is done, now take Kirchhoff's second law, right? Now remaining part is just a calculation part, nothing else. Now see how to simplify this. So this I can write as L di by dt, that is equal to E minus IR. See carefully once. L di by dt is equal to E minus IR. Now this is L di by E minus IR. So this is almost the same as what we have learned while discussing RC circuits, growth of charge, decay of charge. Okay. It is now growth of current and decay of current. So right now it is growth of current. That means current is increasing. Okay. Right. So what else left here? It is only dt is left. I'm take to here. Now integrate. Okay. So now what we are doing here, multiply and divide with minus r, multiply and divide with minus r di upon E minus IR, right? Integration of dt. Now see this becomes minus L by R ln E minus IR, that is equal to T. Now take limits. Current, it is 0 to Y. Now substitute limits and I'm taking this one to here. This is ln E minus IR upon E, that is equal to minus RT by L, right? Now take anti-log both sides. 1 minus IR by E, that is equal to 1 minus IR by E is equal to E power minus, I'm taking this as minus T by tau, where tau equal to L by R. Okay. And we are knowing that whenever you're having e power something, that something must be dimensionless. Okay. That means since it is a time, this also having dimensions of time. Okay. That means L by R is having dimensions of time. Wait. This is not the, this is the tau, which we are calling as a time constant because it has dimensions of time, that we're calling as time constant. It has dimensions of time. We can see in case of RC circuits, RC is known as a time constant. It is now here L by R is known as time constant. Right now, simplify this. From this, I equal to E by R into 1 minus E power minus T by tau. Right? So this is a current as a function of time. Now in this, we can see when time t equal to 0, if I'm taking t0 here, e power, this becomes 1. So 1 minus 1, 0. So I value 0. See carefully the meaning of that. If you observe carefully, we can see the equation. Okay. See this equation, this step. If I'm taking I value 0, E equal to L di by dt. That means just after closing the switch, the EMF induced across the inductor is equal to the EMF of the battery. Get the point? So just after closing, there is no current. Or you can take this as just like an insulator. Okay. Or you can say it is circuit is open. If circuit is open, what happens? Means if you remove this one and nothing is here in this gap, nothing is present, then current cannot flow. That means initially you can take inductor as an insulator. That means no current flows. Okay, right. And next you can see when time t is infinity, it means after a long time. When t value infinity, this becomes now zero, right? That means I equal to E by R, which is maximum current. Yes or no? That means after long time, what happens is there is no fluctuation of current. Okay. Finally, current reaching now one steady state. So since there is no fluctuation of current, inductor has no role. Already we have discussed that role of inductor is to oppose change in current but not flow of current. So after a long time, current is reaching a steady value. Therefore, inductor is just like a conductor, just like a conducting wire. Okay, that's why you can neglect this. So it is only E by R. Okay, so we can keep these points in mind while solving problems and see once what is the value of current when t equal to tau means one time constant. If I am taking t equal to tau, then see what happens. It is E by R into 1 minus 1 by E, right? E by R into 1 minus 1 by E. See this value how much? This will be 0.63 into E by R. That means after closing the switch, or you can say during growth of current, in one time constant, current increases to 63% of the maximum current. Just recollect once RC circuits. Even in that also we have given the same statement, right? In one time constant, charge increases to 63% of the maximum charge. And here also same. So in fact, we can compare these two, okay? And if you plot a graph for current as a function of time, it is again same kind of graph which we have plotted in case of RC circuit, growth of charge, finally reaching a peak value. Okay, right. Now we can focus decay of current. Okay, till now we have discussed growth of current. It is now a decay of current. See here what we are doing. Inductor, resistor connected to one battery. Suppose this is a switch S1. EMF is. I am taking here one extra conducting wire. Extra conducting wire here. It is now S2. So here what I am saying is, till now we have discussed by closing S1 and S2 remains open. So current flows like this, right? In this way. That was growth of current. Now open S1 and close S2. I am repeating now. Now means after current reaches a peak value, that is, so this is N and this is R. What is the peak value of current? I am taking as notation I naught, peak current, that is E by R. After current reaches a peak value E by R, now open S1 and close S2. Get the point. Then what happens is now current starts decreasing. Now current starts decreasing. And you can see initially current was flowing like this, right? Now we are opening S1 and closing S2. Still current flows in the same direction, but now current is decreasing. See the meaning of current decreasing here. Since we have peak current E by R, it means Potential energy is stored in the inductor, in the magnetic field, right? In the last lecture, we have learned potential energy is stored in the form of it is magnetic potential energy that is stored in the magnetic field of the inductor. So we are having here potential energy in the inductor. And once you close this one by opening this, now this potential energy will be lost across the resistor in the form of heat. So current is now decreasing. Y means potential energy equal to half L I square. I decreasing. That means potential energy stored in the inductor is decreasing. In which form? It is in the form of heat across the resistor. Right? Let us now focus. First of all, current is now decreasing here. So we are replacing the inductor with an equivalent battery. So how I am replacing here? I am replacing that a battery now it is like this. See careful. So why I'm taking polarity like this? The reason is that current is decreasing. It tries to oppose the change in current. That means since it is now decreasing, it tries to increase it. Tries to increase means current due to this battery must be in the same direction of the current. That's why I have taken polarity like this. Less, sorry, this is low and this is a high. Okay, right. Now take for this loop Kirchhoff second. So now question is just like there is a battery and a resistor, right? For this. Now see what happens. Suppose we are starting from here. We are moving like this. So we are moving from where to where? From low potential to high potential. Low to high. It is L into, see carefully, I am writing here minus di by dt. The relation is the current is decreasing. Therefore, di by dt itself is negative. Negative of negative positive, right? And we are moving from low potential to high potential. It is a plus. This is a plus L into this one. Next, we are moving along the current flow. So it is a minus IR and this is equal to 0, right? We should be very careful how we are taking minus, or you can say why we have taken minus, because to make this value positive, right? And once you know this equation, remaining just a calculation part, see once. So here what I can write, L di by dt. L di by dt is equal to minus IR, right? From this what I can write L by R di by I, that is equal to, see what else left here. L, I have taken R this side. Di by I, that is equal to minus dt. Now integrate. Now we are integrating. Now see what we get. It is directly first focus limits. Okay. When time t is 0, current was I naught. Okay. At time t, we have to calculate. It is ln I, right? Or if I'm taking limits, ln I by I naught. That is equal to minus t. Okay. So mainly you have to focus how we are replacing inductor with an equivalent battery. And after that, writing the Kirchhoff's second law, that equation, loop equation. If you are able to do these two things correctly, remain only calculation part. Okay. Right. Now I can take this L by R to this side and then take anti-lock. Then take anti-lock. So I by I naught is equal to e power minus t upon tau, where tau equal to, it is R by L, right? What is that R by L? Sorry, L by R, right? Time constant, isn't it? Check it once. I have taken R by L. Yes, R 1 by tau, where tau equal to, it is L by R, isn't it? Which is known as time constant. So I equal to I naught e power minus t by 2. So this is same as what we have discussed in RC circuits. Decay of charge. It is now decay of current. Same graph, same conclusions. We can see when time t0, I equal to I naught, infinity, I value 0, means finally no current. It means there is no potential energy left in the inductor. It is a completely lost in the form of heat. Okay. And next you can see if t equal to tau in one time constant, current becomes, it is 1 by E times of phi naught. That means it becomes how much? 0.37 into Y naught. That means we can say current is decreased by 63% of its maximum value. Same conclusions. Just to compare once with RC circuits. Same graph, same conclusions. Right. If I plot a graph, current versus time. Okay. That will be like this. Approximately like this. Finally touches 0 when t value infinite. Okay. So this is about growth and decay of current. Right. Let us solve problems. See the first question. Consider the circuit shown in figure. Find the current through the battery a long time after the switch S is closed. Asking, after long time switch is closed. Suppose the switch is again opened at t equal to 0. What is the time constant of the discharging circuit? Find the current through the inductor after one time constant. Right? This is the question given. Let us see how to start. So first of all, make the given diagram. It is given R1, R2, two resistors. So they are connected in parallel combination and inductor. Now these are connected to a battery and switch. Initially it was opened. Right, values are 2, R1, and it is cell, and this is given as and taken as C. Okay, battery CMF. See the first question, find the current through the battery a long time after switch S is closed. Long time. So once switch is closed, what happens? Let me calculate first of all current just after closing switch, means t equal to 0 just after closing. Okay, what happens? So we have learned that just after closing, this will be just like an insulator, no flow of current in this way. Get the point. And you can see carefully across R2, EMF is always, or you can say potential difference always equal to E, right? Irrespective of the current passing through this one. See carefully, this R2 is now across this battery, and this is also across same battery. So across R2, potential difference always equal to EMF. Therefore, current will be, it is E by R2. So in this, just after closing switch, and in this, there is no current. So finally, current through battery, it is E by R. And after long time means, after long time, we discussed that after long time, current will be constant. Once current is a constant, inductor is just like a conducting wire, just like conducting wire. That means now question becomes that R1 and R2 are now parallel combination. Therefore, current is now, it is E by effective value. What is the effective value? 1 by R equal to 1 by R1 plus 1 by R2, right? So R value how much? Effective value R1, R2 by R1 plus R2. So E by R. And R value how much? R1, R2 by R1 plus R2 because they are in parallel combination, right? This is after long time. And you can see time constant during charging. Time constant during charging. During charging, see, you can see this battery and R2. This is one separate circuit. Next, this battery and this R1 and L. This is one separate circuit. Both are separate. Okay. So this is here. Growth of current is not depending on the resistance R2 because both are completely independent. See once I can take the same circuit as like this. R2 and sorry, this is a battery. So I'm taking the same circuit as a combination of, I'm taking it as a battery. This is R2 and this is EMF plus R1 and inductor and next battery is like this. So we can take that circuit as a combination of two independent circuits. Okay. So growth of current is not depending on R2. So during charging, what happens? Current is flowing like this in this one. It is simply L by R1 during charging. But if you take during discharge, see during discharge, what happens? Once switch is open, current flows only in this part. Okay, R1, R2, both are involved. That's why it is now L by R1 plus R2 because both are involved, R1 and R2. Current flows only in this part because switch is open. That is the time constant for discharging circuit. And next is asking find the current through the inductor after one time constant. Already we have seen that during decay of current. I equal to I naught e power minus t by tau. After one time constant means it becomes how much? I naught by e. Is a point clear? So like this, we can solve the question. Okay. So one thing, take one more question here. That is, let us do one thing. I'm making a change in the circuit. That is, here taking, I'm taking one capacitor. Okay. Then see what happens. If I take here capacitor, which is initially uncharged. Okay. I'm repeating same thing like what is the current when t equal to 0? What is the current when t is infinity? Okay, like this. So now in this circuit, see carefully, one switch is closed. One switch is closed just after closing. First condition, assume that capacitor initially it was uncharged. Okay, just after closing. This is acting as an insulator. But coming to capacitor, it is acting as acting as a conducting wire, right? That means just after closing, there is no change in the current, right? Okay, next. If you take after long time, so initially current flowing only through in this one, assuming that capacitor was uncharged. Okay, means When it was uncharged, we can replace the capacitor now with a conducting wire. This is what we have learned, right, in RC circuits. Next, after long time, what happens is capacitor will be fully charged. No flow of current in this way. See carefully. After long time, capacitor will be fully charged. Therefore, no flow of current like this in this way. But after long time, current will reach a saturation value, steady value. Therefore, inductor has no role, right? It is just like a conducting wire. So current flows now like this. That means after a long time, current becomes now E by R1. But see here what we got. After a long time, E by R, where R is R1, R2 by R1 plus R. But see here what we got. Okay. So like this, we can expect questions based on RC and RL combinedly in one single circuit. Okay. So I hope you got a clarity.